No, hello guys. I'm Chandramauli, the TA for this CY04 Basic Thermodynamics course. So today I'll be discussing some problems related to entropy and calculation of partition functions and energy and so forth and so on and so forth. So before starting the questions that I have prepared about, can you guys tell me if you have any doubts related to the assignment problem so that if I have not covered them, I'll cover them as well at the end.
Yes, sir. I have some problem.
Okay. Which question?
One, 1, 3, 10, 15.
Just a minute. Mm, okay. 1, 3, okay. 10, 15.
Yeah.
10, okay. And 15. Okay. I've prepared answers for all those questions. I mean, problems related to this. So we'll be covering all this today. Okay. All right, Jaydeep. In that case, I'll get started. Just, okay. Can you see my screen?
Yes, sir.
All right. Then let's get started. Um. Okay. So as you can see, the first question is about energy difference between certain energy levels. So tell me how we will solve this problem. You read the question and tell me what formula to use. You tell me that, then we'll get started. Okay. Which statistics to use? Devi?
Yes, sir.
Okay. What kind of statistics can we use there? Fermi-Dirac, Bose-Einstein, or Maxwell-Walsh? Tell me that first. Okay. See, these are all atoms. Okay. So we are talking just about atoms and not about subatomic particles like fermions or bosons. So what statistics will use?
I think we calculate the fraction of excited atoms.
Correct. So we have to calculate it energy wise, right? So we need to find out
Yes.
the probability of atoms occupying the higher energy level compared to lower energy levels. That is there. So that's why I'm asking what statistics will use. These are like distinguishable particles like atoms, right? So which one? Fermi-Dirac, Bose-Einstein, or Maxwell-Boltzmann?
Maxwell
Yeah,
Ball.
correct, correct,
Maxwell
correct,
Ball.
correct. It's Maxwell-Boltzmann. Okay. Then once we do Maxwell-Boltzmann distribution, so the next is how we'll do. First, they're telling there are two electronic states. Okay. One is sorry, one is the lower level, which they are writing it as S0, 1. So here 0 means the lower energy level, okay, 0th energy level. So 1 means there is only one level here. If there are more number present here in the superscript, that means it is called degenerate. Okay, like for instance, here they have put 3 for the first energy level, it's 3, right? Sorry, okay, okay, fine. So here, as you can see, there are 3. The degeneracy over here is 3. So that means at the same energy level, you will have 3 states. Okay, 3 separate states over here, and they'll all have the same energy of about 159,443 centimeter inverse. Okay, so that's the idea here. So now you tell me how we can write the how we can get the fraction of particles in each of these energy level. You told that we can use Maxwell-Boltzmann. So what is the formula? Last week we did talk about this. Okay, so what is the delta E between between lower energy level and first energy level? All right. So this is the energy difference. So what formula we'll use? Last class I used the formula. Do you remember? N1 by N naught, something like that I used. Remember?
N1 divided by N1 plus N1.
No, that is fraction. Huh? Before that, based on energy.
N1 by N0.
Is equal to what is do you remember this? Okay,
1 by E.
no, we'll go from scratch. So
Oh,
you remember that, probability of any particular state Pi is proportional to e power
yeah,
minus.
e to the power EI divided by KBT.
Yeah. So this you remember, right? So
Yeah.
now let's say I put N1 by N naught. So then what will it be?
Yeah. E to the power minus E1 minus E0
Uh,
divided by KBT.
then,
No, no, no.
okay, fine.
Yeah.
This is N1 and this is N naught. Okay.
Yeah, yeah, yeah.
So now if you do this, then we'll get minus delta E by KBT. Correct. Now what is our delta E now? What is the delta E? 159843, right? And this is in centimeter inverse. And I have so actually Boltzmann constant, it has different units. So I have actually got the number for centimeter inverse and Kelvin inverse already. Okay. So we'll just put that here. 5035. And what is the temperature? 6000 Kelvin. Fine. We have all this. So you first always check the units so that we know that we are in fact putting the correct units in. So centimeter inverse gets cancelled. K inverse and K Kelvin they get cancelled. So exponent it's unitless inside exponential. So that holds good. Okay. So now we just need to use. I'll just use a calculator to calculate this. What do we get? You help me as well. Okay. 159843 divided by 0.69535 into. All right. How much are you getting, Jaideep? Jaideep, 2 point. Okay. So I'm getting this much. Okay. All right.
Yes.
Okay. So this is what I'm getting. So which means that N1 is basically something like this. into 10 power minus 17 n naught. Fine. So this is what we'll be using to calculate the fraction of particles in the first excited state. So now first excited state, as I told earlier, has degeneracy or spin multiplicity of 3. So that means there are 3 equally probable energy levels at that particular energy. So the fraction of particles then will become something like this. Okay. So the total number of particles is going to be n naught is just one degeneracy. So there's nothing, this is one level there, plus 3n1. Okay. So this is how it's going to be, and the total number of particles. Now we need to find the fraction of particle in first energy level. So that is 3n1 divided by n naught plus 3n. Fine. So I'll just put the values, just substitute the values. Okay. So n1 is this much of n naught. So I'm putting that directly here. 17 n naught plus n naught plus this much of, sorry, 3 into 2574 into n power minus 17 n naught. All right. So as you can see here, this number, this is 10 to the power minus 17. This is much smaller than 1. Okay. So the denominator can just be approximated to 1. So that's what I'll do here. What I'll do is, oh, you see, much greater than whatever value we get. What is this value? 3 into 2 point. How much is the value? 12, uh, oh, whatever it is. 12, 21, 22, 20.
6.7722 into 10 to the power
Yeah.
17.
So basically this is what. So what I'm going to do is I'll just approximate it. So it's going to be 6.77. I'll just put it there. Minus 17 divided by this is n naught and divided by n naught. So the fraction is about that much. Okay. So this is the fraction of particles that's going to be in your first excited state. So you see, since the energy difference between the two levels are quite high, you get very less number of particles present in the first excited state. So basically, this means that the ground state is the most probable state. Fine. Do you have any doubts?
No, sir.
Okay, so you understood the idea, right? So you have the probability from Maxwell-Boltzmann distribution, then you calculate the energy difference and go on from there. Fine. We will have similar problems coming up again and again, and a lot of the problems in your assignments are based on this. Fine. All right. So second problem, I mean, read the problem and let me know how to solve it. I'll wait for a few minutes. You can refer to your notes and then tell me the formula for partition function and what kind of distribution will you use. Okay, first tell me what statistics we'll use. These are distinguishable and independent molecules. Okay. So what statistics? Maxwell-Boltzmann or Fermi-Dirac or Bose-Einstein? These are distinguishable molecules. So what do we use? Jaideep?
Maxwell Boltzmann.
Yeah, correct. Fine. We use Maxwell-Boltzmann distribution. Fine. That is correct. So then next step is what are the things we have? So first is we have two states, ground state and a triplet state. Okay. So ground state is non-degenerate. That means there is no degeneracy, there is no multiplicity. So they're telling energy of ground state E0 is taken to be 0. Fine. Then energy of the triplet state, okay? Energy of the triplet state exceeds that of the singlet by epsilon, correct? So what is the energy of for let's say triplet state? I'll put it as E1, okay? What is that? 0
Three
plus, huh?
3 0.
No. So it is 0. It exceeds by epsilon, so it is epsilon, okay? So that's all. Now we'll consider multiplicity and all. So now you see degeneracy of first state, I'll just put it as split state, is 3. Fine, now we need to write the partition function. So how will we write the partition function? What is the formula? First you tell me the formula.
IE into minus EI divided by KBT.
Sigma I e exponential raised to the power ei by kBt.
Yeah.
Correct.
Yeah.
So now here we have two states. One is the ground state and another is the singlet state. So for ground state, there is no multiplicity. So therefore, it's just going to be e power E naught by kBt plus second state, the multiplicity is 3. Okay. Therefore, you multiply the 3 over here and then put ei. Sorry, there's a minus here. I forgot that. Okay. Minus epsilon 1 by kBt. All right. So now they have given temperature to be what they have given the temperature to be epsilon by kV. So we'll use that value also. So this is E naught is 0. So e power 0, that is basically going to be 1. And then 3 into e power epsilon 1 is just epsilon minus epsilon by k epsilon by kV. What is the temperature? E by kV, right? Epsilon by kV. So this is 1 plus 3 into this is just going to get cancelled. So will get cancelled. So it's just going to be e power minus 1. So now what is the value of this? 1 plus 3 into, let's just calculate. 3 divided by e, how much is that? 3 divided by e, around 1.104. 1.104. So therefore the partition function for this question is simple. This is 2.104. Fine. So this is the answer. All right. Did you understand this, Jaideep?
Yes.
Okay. So this is how you write partition function, where you have the energy levels. Okay, minus. No? You have the energy levels, and then you for each energy level you add them up. That's the idea over here, partition. All right. So this third question is again related to calculating partition functions and average energy, So again we are going to use Maxwell-Boltzmann distribution. So here before going into the problem per se, there are two things that are like required to solve the problem. These are just you can consider them like identities. So basically they are it's like sigma, let's say sigma is equal to 0 to infinity 1 by x square xj. Just give me a moment. First identity is 1 plus x plus x square plus x cube. It goes on like this till infinity. Then the formula is 1 by minus 1 minus x. That is one identity that we need to remember. The second identity is the follower is as follows. Is sigma j is equal to 0 to infinity. Okay. J x j is equal to x 1 minus x whole square. Here important thing is x should be less than 1. That's the thing. So these are the two identities we need to solve the problem. Fine. So we'll go one by one. So first thing is system has many energy levels, okay? And the energy of any given energy level, energy of an energy level epsilon j is just j epsilon, okay? Total number of molecule is n. Total number of molecules going to be n. And they have already given that average energy is a epsilon. Okay, so they are asking us what is the formula for temperature of the system. Okay, so since this is I know like distinguishable particle, we are again going to use Maxwell-Boltzmann distribution. Fine. Okay, so now you tell me the Maxwell-Boltzmann distribution. From using Maxwell-Boltzmann distribution, what is the energy value? Distribution. Using Maxwell-Boltzmann distribution. Okay. So first is we need to get the partition function, and then we'll go to the energy level, because if you see here the average value is given like this. Okay, I sorry sigma, let's say j pj and then epsilon j. So this is how it is given, and pj, as you know, it is like this. Epsilon j output. Pj is basically e power minus epsilon j by kBt divided by partition function. So we need partition function one way or the other. We need to calculate that. So first let's calculate the partition function. So partition function is simple. What is the partition function formula from last question you did now?
E to the power minus ei by kBt.
Okay. So what I'm going. So we'll just write everything out. So there are infinite number of energy levels. Okay. So it's going to go from okay, before that we know epsilon j as well. So I'll write what is epsilon j from they've already given, right? See here. Epsilon j is nothing but j e. So it's going to be like this minus j epsilon by kV. Alright. So here if you then what we'll do, we'll just write out. So let's say when j is 0, so it's going to be e power 0, which is 1. Okay, maybe I'll put it as 1. E power 0. Next is e power minus epsilon by kVt plus e power minus 2 epsilon by kVt plus next is e power minus 3 epsilon by kVt, correct? It goes on like this, okay? Simple, because we are just summing over j, we just need to substitute everything with j. Then if we keep going on, it's just going to be 1 plus e power minus epsilon by kVt plus e power minus 2 epsilon by kVt, like that. Now what we'll do is, let I'm just going to do mathematical substitution, okay? Let e power minus epsilon by kVt be equal to x, okay? Then when we do that substitution over here, q becomes x plus x square plus x cube, like that. So then we can use the above formula, okay? See, this formula we can use now, okay? 1 plus x square, x plus x square, x cube, like that we can use this formula. Then that formula is simply 1 by 1 minus x. Then we substitute back our e value and then get the actual partition. Okay, so then it will be just 1 minus e power minus epsilon by kT. Alright, so this is our partition function. We have got the partition function now. Next is we have to get we know the average value, we need to evaluate it. So as you know, average value is going to be 1 by q sigma j, going to be epsilon j e power minus epsilon j by kV. So this is the average value. Fine. And the average energy is already given over here, as you can see here. Average energy is already given, A epsilon. Okay, we are just going to use that over here. A epsilon is going to be equal to 1 by q. We'll just keep it as q for now. 1 by q. And then what is Ej? That is nothing but j epsilon. So j epsilon e power minus again j epsilon by kVt. As you can see here, epsilon is equal to 1 by q. This epsilon is common, so I'll take it out. Yeah. J e power minus j epsilon by kVt. So now this epsilon and this epsilon will get cancelled. Then epsilon is equal to 1. Sorry, A, no? A by 1 by q sigma j is equal to 0 to infinity, right? That's what that many energy levels are there. J e power minus j epsilon by kVt. So this again is like this formula. The hint that I have given, j x power j. Here x will be e power minus epsilon by kBt. Okay, so same thing we'll use here. We'll just push this down a little bit. That formula only we have to use. It's going to be 1 by q then What is the formula? X is e power minus epsilon by kbt divided by 1 minus x whole square. No? So 1 minus e power minus epsilon by kbt whole square. I'm using this formula, okay? 0 to sigma j xj is equal to x y and minus. I'm using this identity to solve the problem where x is equal to e power minus epsilon by kbt. If you have doubts, you just substitute and see, you will get this. Okay. Now a, what is q? Q, we know that it is 1 divided. Just what I'll do on this step only, I'll take q to that side. So a q is equal to, okay. Now what is q? We know q is 1 by 1 minus e power minus epsilon by kbt. So that we know already. By kbt. After this is just solving like equation in one variable, single variable. Like that. So this and the square will get cancelled. Then I'll multiply this. I'll just cross multiply this. A minus a e dt. We need to find t, right? So I'll get all epsilons and answer. Then a is equal to, this goes a 1 plus a by e power epsilon by kbt. So then it becomes e power minus epsilon by kbt. Okay, now we can just take logarithm of this. Then we take logarithm of that. Ln a by 1 by a is equal to minus epsilon by kbt. Okay, so then I'll take t to the left. So t is going to be equal to minus kbt and then this will come below 1 by a by 1 by 1 plus a. So we can still, I mean, we can take the negative inside and then invert it, that we can do. So epsilon by kb logarithm of 1 plus a by a. Then it's just simple mathematics. Then t is equal to epsilon by kbt kb then 1 by a, 1 plus 1 by a. Okay, so this is the final temperature. Fine, this is what we wanted. So see, this might look complicated and all, but it's very simple concept based on two things. One is average energy of a system that follows Maxwell-Boltzmann distribution is the following formula, where average energy is equal to sigma Pj and Ej. Simple. This is the formula for all the average energies in a given statistical mechanics system. Okay. So then partition function is again sigma j e power minus epsilon j by kbt. So these two things, if you know, you can solve the problem. All right. Other things are just two mathematical hints that are required to solve the problem, which we may not be aware of as we come out of school immediately. So that's the idea. Okay. Do you have any doubts here, Jaydeep?
No, sir.
If you have any doubts, you let me know. Just take your time, think about it. Okay, fine. Then we'll move on to the next problem. So read the question and tell me. This is a very straightforward question. You just tell me directly. They are also given the number of microstates. So you tell me. Okay, what is the entropy formula when microstates are given? Is equal to what? Kb ln W. Correct. This do you know?
Yes, sir.
Okay. So now you tell me for both the systems, how will you do? For S1, for system subsystem A1, what is the this thing? Just put S A1. What is the value now? Kb ln what? W1. Okay. A2 is equal to Kb ln W2. Okay. Then for combined system where S is A1 plus A2, you just add the entropies. That's all. Fine. You don't have to worry about anything else. So it's basically going to be Kb ln W1 plus Kb ln W2. That means it is Kb ln W1 into W2. Okay, that is the law of logarithms. So what is the value then? Let's substitute the values. What is W1? 10 power 20. This is 2 into 10 power 20. So 1 into 10 power 20 into 2 into 10 power 20. How much is this? Kb ln 2 into 10 power 40, which is nothing but ln 2 ln 2 plus 40 ln 10. Therefore, combined system entropy of this combined system is substitute ln 10 to 40 plus ln 2 is 92.8 kb. Okay, that is the answer. Okay, is there any doubt in this question? Really?
No, sir.
Okay, if you're clear with that, then we can go to the next question. See, next question is just direct application of binomial theorem. Do you know binomial theorem?
I studied in class 11 in
Huh?
this topic.
Did you go?
Study,
Did you? Yeah, yeah. Did you go through the lectures?
yeah,
Okay, in that also sir told. Okay, fine. See,
study
first is
school.
total number is n ion channels. Okay, and the probability of open ion channel open ion channel is equal to Q. So what is give fraction of time that any one protein is open to allow ions to flow through is Q. So now what they want is, what is the probability that M out of N channels will be open at any given time? So it's a direct application. Okay? P, M, N. How can we, what number of ways we can choose M from N is N, C, M. Okay, that you know. So then probability Q, and how many are open? M are open. And what is the probability that it is closed? 1 minus Q. It could either be open or closed, right? That's the thing. If M are open, then how many are not open? N minus M are not open. So that is the formula. Simple. Okay. This is what you need to do. Do you understand this?
Yes, sir.
Okay. In that case, we'll go to the next problem. As you can see here, this is again simple probability questions only. So let's say we'll say probability of ordering takeout is equal to 30%. 30% is what? 0.3. Okay. So if they're telling that, so out of entire customer base, those who are choosing hamburger, those who are choosing hamburger, takeout, see, takeout and hamburger, takeout and hamburger is 8%. That means 0.08. So how do you calculate and probability?
NCR.
No, and probability. See, and probability, you just need to multiply the individual probabilities. Okay. So they are asking us to calculate the probability that a customer who orders takeout will order a hamburger. That means they're asking probability of hamburger. So it's basically this. Takeout and hamburger is basically simply takeout into hamburger. What we want is hamburger. Okay, this is what we want. Then after that it's just simple 0.08 into 0.3 into hamburger. Now what we want? We want the probability of hamburger. So probability of hamburger equal to 8 by 30, 4 by 15. So that is the value. Okay. Therefore, probability of hamburger is equal to, what is 4 by 15? Put the value. 0.27267, 0.267. Okay, so that's the value we are after. All right, you got the idea?
Yes.
Okay, next is see, there's a similar problem in the assignment, so you will have to use similar concepts and then give your answer. Okay, so now the question is, there are n non-interacting particles. They are distinguishable particles. So distinguishable, therefore we have to use Maxwell-Boltzmann distribution, or simply easy formula that we already have. So now they are in thermodynamic equilibrium and they have particle of spin 1. What is the entropy of the system? So what you need to understand is, when any particle has spin 1, which it means they have 3 states. Okay, they have 3 possibilities. That is the That is a tricky part here. You need to understand that. I mean, you need to know that to solve this problem. Three possibilities. It can be plus 1, okay? It can be minus 1, or it can be 0. So these are the three possibilities that any of this n particles can take up. Okay. Once you know this, then it's easy. So all these are non-interacting and they're distinguishable particles. So what is the total number of possibilities now? There are n possibilities, n particles. So then total possibilities for each particle, it can take up any of these three. So now it's like head or tail, na? You have head or tail, two possibilities, and then you have n number of tosses. Okay. So then what are the total number of possibilities was? There it was 2 power n, right?
Power n.
There. Here we have three possibilities instead of two. So what is the formula?
3 power n.
Correct. That's all. So now you have this. So what is the entropy formula now? S is equal to what? Two problems back we wrote now. KB, L and W. Huh? So this is KB, L and W. So this is just KB, ln 3 power n. Fine. So that means S is equal to n kV ln 3. So that's the answer. Okay, understood.
Yes.
Okay, if you're clear with that, we'll go to the next question. So now we have few things. We have two parts to this question. We'll solve one by one. So first, there are n sites. Okay, I'll just write as there are. Let's put like this. There are n sites. This is a lattice, so n sites here. N sites, and there are n particles, small n particles. Okay, there is another adjacent lattice which is not connected to it. Here there are, let's say, m sites and small m number of particles. Okay. So this small m and n, they cannot go to other lattice. They are not connected. Okay. So now this is called state A. So they're asking what is the total number of configurations in WA. Simple, okay? So how will you solve this problem? So first we'll do one by one. Just tell me what are the number of ways you can choose small n sites out of n sites. Huh? How you're choosing small n sites out of a total number of capital N sites. What is the formula? N choose small n, right? Correct.
Yes, sir.
So for this lattice, how will it be?
M choose small.
Yeah. So now we just need to combine these two. For every one configuration here, all these m choose small m configurations are possible, and vice versa. So we just need to multiply them. So WA is going to be NCN into capital M CM. Simple, right? So it's just going to be M So that's the formula. Okay, this is the answer for WA. So that's simple. Okay, so now the next thing is the now what they're telling is both n sites and capital M sites. So this n sites and M sites are joined together. Okay, so that means total of n plus M sites are available, and there are n particles and M particles, and they can take up any state. Okay, they can go to any place. Both states are accessible. So they're asking us what is the for this configuration, what is the number of this thing. So for WB, it's going to be simple. So first, let us choose n for n particles. So out of a total of all the states are available, all the lattice sites are available. Okay. So from a total of n plus m sites, you choose n particles. Okay. And then remaining how many sites are there into n plus m minus n. Out of that, you choose m sites. Okay, because for m particles you have only left these many sites. You don't have all the sites, so because already n sites are taken now. So now
Yes,
this
sir.
so now this factorial divided by n factorial. This is n plus m minus n factorial into n plus minus n factorial divided by n factorial divided by n plus m minus n. Now this and this are common. Just cancel them. Finally, we have WB is equal to n plus m factorial divided by factorial factorial n plus. Okay, so that's the final answer. Did you understand this much?
Yes, sir.
Okay, you have understood, then we'll go to the next problem. Okay, here what we have is we have a six-sided die. Okay, normal dice. Okay, so then what they are asking us is that we have to roll it in as many times as required to ensure that a 4 occurs. Okay, so what they're asking is what is the number of rolls k that is required to ensure that the probability of getting a 4 at least once is 2 by 5. So that's what they're asking. So first, what is the probability of getting a 4 when you roll a dice 1? Okay, one dice roll. What is the probability of 4? 1 by 6 na?
1/6.
Huh. Probability of not 4?
5/6.
Okay, 5 by 6, correct. So now what we have to do is we have to choose 5 by 6. I mean, we have to get 5 by 6 such that it is at least less than 2 by 5. So now let's see. We need to multiply it. Wait. So let's say all these are independent rolls. So this is one dice roll. Let's say for two dice roll, what is the probability of not getting 4?
10 by
No, no. See, 5 by 6. raised to the power 2. Okay, simple. We just raised to the power 2. See, for two rolls, p naught 4 is equal to p 5 by 6 raised to the power 2. So then for 3 rolls, it's 5 by 6 raised to the power 3, like that. So for k rolls, we need to find k. For k rolls, p not 4 at least once is 5 by 6 to the power k. Okay, all right. So now what they're telling us is we have to get the number where at least 2 by 3, at least 1 will appear. So total probability is always going to be 1 minus 5 by 6 to the power k. This is the probability of not getting a k. Okay, 1 minus probability of not getting a k means probability of getting a 4. That should be greater than or equal to 2 by 5. That is the way we are going to do it. So 1 is the total probability. 5 by k, 5 by 6 to the power k is the probability of not getting 4 at all in any of the rolls. Okay. Then 1 minus this is going to be the probability of getting a k at least once. Do you understand this part?
So can I explain this?
Yeah, I'll explain. Which part did not understand? You didn't understand this power part or this second part?
The second part.
Huh. Okay. So the probability of not getting a 4 even once is 5 by 6 to the power k. This you understood, no? Out of k rolls.
Yes, sir.
Huh. So this is, you're not even getting any 4. If you get at least one 4, it will not be in this probability, correct?
Yes, sir.
So 1 minus this value is going to give you the probability of at least getting 1 4. Okay.
Yeah.
So this is basically what? This is basically means probability, because 1 minus something is the other probability, na? Probability of at least 1 4. It could be even all 4s, okay? But it's at least 1 4. Because 5 by 6 to the power k is not getting a 4 at all. Okay. So now we need to solve this problem. Take this 3 by 5. Then we have to take a, now we'll take a logarithm. 5 by 6 greater than or equal to 3 by, ln 3 by 5. Ln 3 by 5. So let me just get the values. Just give me a minute. There is a small mistake here. This, we are adding we are adding we are adding we are subtracting one from both sides. Wait, give me a minute. Not exactly this. We are subtracting -1 from both sides. So this will be minus. Then we multiply by -1, then the signs will get changed. By 5. Now you take logarithm. Now let's take ln 5 by 6. So this is minus 0.18 k is less than or equal to ln 3 by 5 minus 0.51. So again we multiply by minus on both sides, the signs will get changed. Divided by 0.18. This should be greater than or equal to 2.8. Okay. So that means what is the next whole number? So the value is k is equal to 3 because it should be greater than that, and that's the round number. We cannot have 2.8 die rolls. Huh? So this is the value. You got this idea, right? Got the essence of the problem? Did
Yes,
you?
sir.
Okay. So then in that case we'll go to the last problem. Huh. So here again it's going to be simple. We need to find the average energy, follow something for a 3 energy level system that follows the average. Okay. So first what we'll do is we'll write down the average energy formula. What is the average energy formula? We wrote before, right? Sigma I Pi Pi Ei. Correct. This is correct. This is the formula that we wrote before. And
Yes, sir.
what is Pi? It is going to be e power minus epsilon I by kVt by q into epsilon I. So what we'll do is we'll first calculate all the PIs because there are only 3 levels. So first we need to calculate the partition function. So what is the partition function? Sigma I e power minus epsilon I by beta k beta. Okay. So first there is what is the energy level? First energy level degeneracy is 2. So that means 2 into e power energy is 0. Okay. So I'll just put it as 0 directly. Plus next is degeneracy is 3. So I'm going to multiply it like that. E power minus epsilon 2. Here energy level is 2 now by kVt plus here energy degeneracy is 1. So you can stay like that. So epsilon 3 by kVt. Now we'll just substitute values. This is just 1. So 2 plus 3 into epsilon. My E2 is kVt, just kVt. So minus kVt by kVt plus e power minus 3 kVt by kVt. Okay. So then we can just calculate this. This is just 3 power minus plus e power minus 3. So we need to get the values. So I'll just calculate the values. 3 divided by e plus e power minus 3 plus 2. This is going to be 3.153. So this is a 15334. So this is the partition function. Okay. Now we got partition function. Now we'll have to calculate the probability. Okay. So P1 is what? What is the degeneracy? 2. 2 into what is the energy? E power minus epsilon 1 by kVt by the partition function. So epsilon 1 is anyway, as you can see, it's 0. So it is going to be 2 into e power 0 by q. It's going to be, this is just 1. So 2 by 3.1534. So what is the value? 2 divided by 0.1534. This is something like 0.634. Okay. Now similarly we have to find the Q for other two things. So here is going to be equal to minus epsilon 2 by kBT by Q, which is nothing but 3 epsilon I divided by Q. What is that? Divided by this. So 1.104 divided by 3.1534 is equal to 0.35. Okay. Then P3 is equal to, there's just one level. So e power minus epsilon 3 by kBT divided by Q is e power minus 3 by Q is e power minus 3 divided by 3.1534. It's around 1.015, around 6. Okay. Now what you have to do is just check if the probabilities are correct. Okay. Now what I'll do is I'll add all these three values. 0.0163 plus 0.634 plus 0.35. It's coming to 1. So that means the values that we calculated are indeed correct. So we have the probabilities. No, we just need to calculate the average energy. Once again, I'll write the formula I P I E I. So what is the P1 E1 plus P2 E2 plus P3 E3. Okay. So what is P1? 0.634 into 0. Correct. Value is 0 there. Plus 0.35 into, what is that? Just 1 kBT. So kBT plus 0.016 into 3 kBT. What is this now? 0.0163 plus 0.35. So this average energy value is coming to around 0.398 kBT. So this is the average energy that we got. Okay. So this is how you have to solve the problem. You got the idea? Do you have any
Yes, sir.
doubt here?
Sir, in first step, can I explain it?
This step, huh?
Yeah.
This partition function step.
Yes, sir.
Okay, so see, partition function is basically you have to take the energy of each of these steps now. So first energy level has degeneracy 2. That means what? There are two levels, like, okay, so it's like this. Okay, there are two levels at energy level 1 itself. Okay, that's why I'm putting 2 here. Two states with energy level 1. Okay, so then second energy level has 3 states. That's why I'm putting 3 over here for this energy. Then last thing, that's just 1 energy level, so I'm just multiplying by 1. Okay, so that is what we are doing here. Each energy level, so first energy levels energy is 0, so e power 0. Okay, then second energy level 3 is the number of degeneracy into e power, I'm putting here minus kBT, no, so minus kBT divided by kBT, that's 1. Here third energy
Oh,
level,
sir.
I'm substituting this minus 3 kBT divided by kBT, that is e power minus. Okay,
Okay, sir.
so you understood all this, no?
Yes, sir.
Okay, if you have understood, so that's it from my side. I think I've covered all the problems that you already told that you wanted to discuss in from exam. I mean, from the
In
assignment problems.
exam in 11, can you explain?
11,
11.
11, 11, 11. Just a minute. 11. So 11 is just, see, 11, it's just a direct question, okay? Direct, what is it? Direct formula. You just need to apply the formula. So there are three options there. One is Maxwell-Boltzmann, one is fermion, one is for bosons. You refer to the notes, it's just direct formula. There's nothing difficult to that.
Okay, sir.
You refer to the class notes, it's there in the class. Okay?
Okay, sir.
Okay. Do you have any other doubts?
No, sir.
Okay. In that case, that's it from me today. Thank you for joining.
Okay, sir.
Okay, see you. Bye.